So now we want to talk about L2. This is the influence or boundary conditions. Boundary conditions in the column. Okay, boundary conditions. And what happens is this, okay? Watch this. When I have if I were to look at, and I'm just going to do this, I'm not going to derive it or anything. I'm just going to do it anecdotally, okay, here. When I have if we recall our pin column right here. And if I look at, this pin column like this right here, you would say and it buckles. So we have some critical load applied, P critical, and it buckles out like this. Bam. Okay? It buckles out. The initial length of this was L. Okay? The initial length was L. The buckled length. The length of the buckled length, right here, from here to here, from 0 to 0, okay? From 0 displacement to 0 displacement, that buckled length right here was also equal to L. Okay? And this would have what's called an effective length factor K equal to 1. Okay. All right. K equal to 1. Now let me show you another one. Okay, that way without having to derive this. Let's take for instance a fixed, like a flagpole, fixed cantilever sticking out of the ground. So here now I have a cantilever and it's stuck in the ground right here. And I have here, I apply the critical load to this cantilever. I have this length of my cantilever here, L. Okay. Oh, I'm going to need some more space. Oops. Oh, this is not going to be pretty. Okay. But my buckled shape, you can imagine if I check this out right here. If I kind of fix this right here and I apply it, it kind of does that. Yeah? Okay, right there. So it goes like this. Okay? That it looks like this. This is my buckled shape here. And what it is here is it's like I need to do I had to complete the curve, if you will, right? And so really the rest of it would be like this right here. Okay? To complete an entire buckled length, what does it take for me to do that? And that would mean that I have this L and this L right here, and this buckled length, my buckled length in this case, is 2L, which means that I have an effective length factor K of 2.0. Okay? 2.0, right? 2.0 there. Do you think it's easier to buckle? Which column do you think is easier to buckle? The top or the bottom? Which column do you think is easier to buckle? What do you think will take less force? Me, if I hold it like this, or if I just hold it at one end like this? Yes. Yes. That's just the length of the column. Yeah, we're gonna get there in a second. Okay, and then so here, which one is easier to buckle? You think? This, the flagpole, or the pin? The flagpole. The flagpole is easier to buckle. Okay, you try it. Just hold a piece of paper right here, like this, and then it'll buckle on its own, right? And then if you hold it like this, it won't buckle. Okay? Yeah? Okay? By its own self-weight. All right? So here, okay, so you expect the critical load to be less for the bottom. Yeah? Right there? So the equation for the critical load is this. Pi squared EI over KL squared. This is our critical buckling load equation that we are going to use. And K, the effective length factor, depends on the boundary conditions. This is how we account for our boundary conditions. When it's pin-pin, K equals 1. When it's a flagpole, K equals 2. You can look at figure 13-10 in your textbook, and you will see all kinds of examples of K that you're going to use, okay, to calculate the critical load. All right. Okay. That's it. Any questions about this? All right.